Okay, so we're going to look at Lisp, and I've already given you a tour of Lisp, and you've started on your implementation, so you understand Lisp to some degree there. And if we were to just look at programming in Lisp, that introduction I gave was probably enough for you to go to the Common Lisp manual and go and understand how Lisp works. Okay. So what's going to be different in what I'm going to talk about is that I'm going to actually talk about implementation. Okay. So we've got now a variable supporting interpreter. Okay, so A1 was a basic interpreter, and now we've got A1++, one step more, we can set variables and look up variables. Okay, so the next step is a Lambda supporting interpreter. Okay? So this Lambda expressions that Java has and other languages today that also have functional aspects have. So we want to go and understand Lambdas, so we're going to implement Lambdas here. Okay, so we are going to, of course, evaluate variable atoms. We're going to also now have Lambda expressions, and this is the form of a Lambda expression. And here's an example of a Lambda expression. So so there are two things we're going to do: Lambda expressions and Lambda expression applications. Okay, so a Lambda expression is just going to be of this form. I have given you an example here, and we can go and dissect this example. And the Lambda expression form is the example is below, and on top is the general form. So we've got a list. A Lambda expression is a list that begins with lambda. Okay, and then we have P1, P2 to Pn as a sublist there. And based on your knowledge of Java-like languages and other languages, P1 to P1 will be called what? So parameters or formal parameters. Okay, there's formal people distinguish between parameters and arguments, and lots of other people don't. So we'll be formal and call these formal parameters. Okay, and those are the variables essentially. Okay, and the values to which they are assigned are the actual parameters. And OE1 to OEN are basically optional expressions that are in the body. Okay, so you may or may not have these. You may have n equal to 0. And the Lisp I had learned never had OE1 to OEN, or at least I never saw an example of that. But we do want when the lambda body is evaluated, we want some value returned. So we do need an expression that is returned, and that I'm going to call the return expression. So we do want a return expression, but before that we might have some optional expressions. And in the example I've got, we see that x and y are the formal parameters, print x is an optional expression, and plus xy is the return expression. Okay, so that's a lambda. It's a basic function definition without a name. Okay, we saw that before, and we're seeing this a little bit more formally now. Okay, questions so far? So that's one kind of new expression we have. What do you do with lambdas? You apply them to actual parameters. Okay, so we also have now our function application is going to change. Our function application used to be function identification with E1 to En as being the arguments, and the function identification was an identifier atom. Now this is a bigger headache. Now the function identification can be a lambda expression or something that evaluates to a lambda expression. Okay, for now we'll just say that it can be a lambda expression. So this F is now more complex. It's either a previously discussed identifier atom or it is a lambda expression. Okay, and here's an example. So the same lambda expression we had before, but that is enclosed now within another list, and it's the first item of that list, and the remaining items of the list happen to be the actual parameters or the arguments, as you might call it. Okay, so let's go and see the structure here. Here's the lambda application. We put the lambda expression within another list, make it the head of the list, and then we have E1 to En be the actual parameters. Okay, so that's the structure. That's what we input. Our job now is to take these inputs, convert them into S expressions that are internally stored, and define an appropriate eval to get that stored. Okay? Questions? Okay. So, do we have to do something to our environment? Okay. And I'm kind of claiming through this slide that I have two kinds of scopes. So let's look at it. I can do setq x10. Okay, and we know that in the environment x should be bound to 10. That's one scope. And what's the other scope here? Check it. The lambda itself. Okay, the formal parameters define variables, and they have to be bound to values. Right? So when we evaluate this lambda expression, before we evaluate it, we know x is 10 in our environment. Can we just change that binding of x10 with x4?
I don't believe so, no. If you wanted to have it remain constant, they're outside of each other's scope.
So they are outside of each other's scope. So you're saying the global variables, there's two scopes, and the x that to which 10 has been bound is not visible in the lambda. Okay. But it has been, what's the technical term for something that has, it could be, you're saying it could be because if, sorry? If it has not been shadowed or hidden by the lambda variables. Okay? And the question is, once we've gone and executed the lambda expression, if I go and do print x, can I do a print x? And what the value will be? And the value is, the old value. So I can't replace x10 with x4. If I destroyed it, I could, but I don't want to destroy it. Okay? So we need now we see the need for nested scopes. Right here. Okay? So lambda application pushes and pops a scope in the environment. Okay? And if you've done compilers, that corresponds to what? Sorry? So it corresponds to pushing and popping a stack. Typically we go and push and pop stacks, right? So is this pushing and popping equal to the same as pushing and popping a runtime stack? If it was, then I wouldn't ask you, have you done compilers? With that you have to know if you've done recursion of any kind. So when you open a curly brace when you're programming, and if you've done compilers, you push and pop definitions in the symbol table. Okay, you may not actually go and create a new, you might actually just take X and add something ahead of it. But essentially, when you open a scope, you're creating essentially a new symbol table over the existing symbol table. And when you get out of the scope, you're popping the symbol table. Okay? We will see later that there are versions of Lisp, the Lisp I learned, where indeed the stack kind of pushing and popping also applies to scopes. Okay? But for now, this is defining scope and not the calling stack. Okay? So this is where you're defined. So lambda x, this lambda expression is defined within the global scope. So essentially, we've introduced a new scope within that scope, a static scope, not a dynamic scope. It's not a call scope. And stacks have to do with calling order. Okay, but like I said, Lisp actually allows dynamic scopes to also dynamic. It also allows dynamic scopes. Okay. So we need now, before we go and look at how we're going to evaluate lambda expressions, let's get our environment right. Okay. And once we get the environment right, hopefully our expressions evaluation will be easier. So my scope will not change. Okay, my scope is a hash table. It's got, for now it's a hash table. It'll have multiple hash tables later, but for now we still need a single hash table. Well, what's going to change is the environment. Okay, and okay, so how should we change the environment? So to accommodate lambda expression evaluation, and I've kind of told you that already, but let's get the answer back from you. What do I need to do now? What kind of data structure do I need now to have nested scopes? So a stack. Okay, so I can just have a list. I can just have a list of. I can have a stack of what? Scopes or environments? You think?
Probably scopes.
Probably scopes. Okay. So now your code all has this environment data structure in it, and we don't want to go and change that to a stack. Okay. So it was a little tricky to be upward compatible here. And so what we do essentially is we can go and take the current environment, and how do we, so we don't have a separate stack entity. We take the current environment, which is like a stack, with the scope being in it, okay? And we allow an operation called new child, okay? So that is like saying push a scope. And what that does is create a new environment that points to the previous environment. And that new environment has got a get parent where you can go to the next element. Okay, so we need a stack of scopes. So we also need to follow from inner scope links to the outer scopes. So we need links there, and so that's a data structure, and that environment will have its own scope in it. Okay, so this is how you get basically a linked list of scopes, and we'll actually have a tree of scopes. So we won't have a stack. As we get ambitious, we're going to have a parent with multiple children and multiple stacks existing at the same time, and that actually is consistent with parallel programming, because parallel programming has multiple stacks, and if the inherent data structure has got a tree structure, then we can go to parallel programming much easier. Okay, so that's for later, but I'm just trying to tell you what will come later. Okay, so we're going to have a tree. For right now, it's a linked list, but later we'll have a tree. Okay, when we want both dynamic scoping and static scoping, we'll have a tree. We'll have all kinds of scopes hanging around. Okay, and so that's the data structure we'll have. Okay, so the new child and get parent are given to you. In the abstract environment class that you're given, these are implemented. So you don't have to worry about what they do. I mean, you have to worry about it from a conceptual point of view, but not from an implementation point of view. So our job now is to define lookup and assign, given that now we have this linked list of environments. Okay? Questions? So changes to lookup and assign. Our get and put won't change. Okay, and the get and put actually are something that the environment also has. Okay, so the environment delegates to the scope and have its get and put, and at some point we're going to also change the put. Okay, but for now we have to just worry about lookup and assign. And to make our life easy, we'll assume that the lambda body does not invoke setQ to change its parameters. Or even globals for now. Okay, globals, we just won't deal with that problem right changing values of parameters is a really bad programming practice because suddenly that variable is also the value that you came in with and you're also changing it, so it becomes confusing, especially if these are not reference parameters, which we'll talk about later. But Lisp allows you to do that. Okay, at least C Lisp does, but it's very contrary to functional programming. Okay, so for now we are being very functional. Okay, so that's the rules of those are the rules of the game. So as I said, we have scope.put and scope.get. We have multiple maps. For now, we're just talking about the identifier map. Okay, and we're just going to use the get input of that map. And environment just does the get scope, get and get scope put for its get input methods. Okay, so that we are not changing for now at least. We have to change assign and lookup somehow. Okay, and the question is how. So let's begin with this. Let's go and first say that, you know, I'm just going to have assign do a put. Okay, so, and I'm going to have lookup do a get. Okay, I said they must change, but in this my first try at it, I don't change. If I don't change, what's going to go wrong? So, so will the assign work, by the way? You're talking the lookup, right? Will the assign work? So when will you assign when will you assign in a lambda body? When it's when it's formal parameter. We've already decided that at the start of at the very start we will do it. Before the body is evaluated, we'll go and assign once. We won't assign later. Okay? And we certainly are not assigning to global variables. So our assign is simple. I made the rules easy for us. Okay? And assign will indeed do what I've got here. Given the rules. When the rules change, we have to change assign to. And with the lookup, you're saying that if I reference a global variable, if I go in the example I gave, it will work just fine. Because we only referenced our local parameters in the function body. But as Sam mentioned and as other people said, we should be able to reference the global variables too. Okay? So we are not going and looking up the parent. Okay? So what should I do? I mean, should I even do so in what order do I look up and what should I do next? So this is my initial code. What should I do? Until you find it. So I first try to get it in the current scope because that shadows. And so only assignment lambda is to local parameters once, no set q, no assigned. So that's a change. I go and check if the retval is null or not. Okay. And if it is null, I do a get parent dot get. Otherwise, I return the retval. Don't be too quick to shake your heads. Yes. I always put a little bugs in my code. So what's wrong with this? My lookup is calling, yeah, Robert. Oh, sorry. Yeah. So, yeah, that's true. Exactly true. So you might not have a parent, in which case we're in trouble here. Good. Yeah. So Robert considers the case where we have the bottommost scope, okay, and you're considering the case where you have more than two scopes. You're not giving so for two levels it'll work, right? So if you have three levels, For one level, it won't work, right? Because what Robert said. For 2 levels, it works right. And for 3 levels, it won't work right. Okay? So we don't want to call get. We want to call, when greater than 2 scopes, look up. Okay, and I won't, I'll assume that the get parent thing will just return null somehow. I wish I had a better if statement in Java to make that more concise. It's a challenge to go and write small pieces of code with this animation. Okay. Okay. Can you have more than 2 scopes in Lisp? I mean, have you studied enough of Lisp to imagine more than 2 scopes? Gosh, you think yes? Yeah. So we know that set Q, that is 1 scope. Lambda xy, lambda expression is 1 scope. How would I get nested scopes? So we can nest lambdas. Okay. So remember, lambda has a body. And since we can apply lambdas, since we can pass parameters to lambdas, the body of an outer lambda can call an inner lambda. Okay, and the inner lambda can shadow variables, so basically we have to deal with the situation too. Okay, so x is being shadowed twice here. So that's okay. So that's why we need the get parent. Okay, we've got the environment. Keep going. Now our challenge is, so we have a new environment with nested scopes. Okay, and now we have the environment has got some new methods, new child and get parent. Okay, and our job is twofold. We have to evaluate lambda expressions, just lambda expressions without any arguments. And then we have to evaluate lambda applications. Okay, so you see both examples here. You see here lambda, just a lambda expression. You can type that in, and it prints back what it saw. And then we have a lambda application. Okay, so we have to deal with both of these cases now. Okay, that's our job. Once we deal with this, function implementation is easy. Okay, this is the basic concept of function definition and application. Okay, so function definition we have to deal with, function application we have to deal with. Function definition also happens to be an expression, so both of them are expressions. Okay, so you deal with eval lambda. So we have these 2 cases: eval of lambda expression, which is the definition of a function, and eval of lambda expression application, which is an application. So let's enter the first case first. And before we evaluate it, so we have to return back an object that represents our function definition. That's what evaluating a lambda expression means. Okay? And we have 2 kinds of objects. It's got to be an S expression, right? Everything is an S expression in Java. So we have 2 kinds of S expressions, atoms and non-atoms. The object you get back, the S expression you get back from a lambda expression, you think is an atom or a composite? A composite? It doesn't seem, it's not a string, it's not a literal, it's not an identifier. It's got this, it's a list with lambda, another sublist xy, and then a body. So you would say, so certainly what we input is a composite. The question is what you get back is an atom or not, right? And we know that atom has got a get value in it with it, and composite has got a get head and a get tail. Okay, so we don't quite like it being an atom because there's a list, But Andrew, you disagree? So this is just a lambda definition. This is independent of what it's doing, and Lisp doesn't know what it's going to evaluate. Lisp can't look into the code and evaluate, and it's possible that a lambda expression evaluates an atom sometimes, and it evaluates a list sometimes. It can do that. Okay. So we don't feel comfortable with an atom because it's a list, but atoms are responsible for eval. Atoms are responsible, so are composite expressions, and atoms are responsible for get value. Okay, and composites are responsible for get head and get tail. What would be the get head and get tail of this? And when would you take that? So if we were to define a get head, what would be the get head of this? Of not the input expression, of the return expression, what would be the get head? You're a language designer.
I guess one thing you could do is make the head a list of the arguments.
You could make the head be the list of arguments, and the tail be the body. So in that case, you really are interested in the arguments and body, right? You're not just treating it as a get head and a get tail kind of thing. Okay. So if you evaluate this, you actually get true. Okay. It's basically saying, get head and get tail are just not right things here. Anything that doesn't have anything that we don't want to decompose into head and tail, we'll call an atom, because we are not dividing it. Okay? And so we have to create, as a result, we have to create basically an atom object. Okay? So, and this is what I'm saying here, that if you do a car of lambda P1, P2, Pn, you shouldn't really, it doesn't make sense. If you're doing the car, you're really trying to do an application and you're trying to get the parameters, so we'll just define some extra methods for that. So these won't be allowed. Get tail and get head won't be allowed. But we do need a lambda for its application. So we'll have get arg names be this extra method. Okay, so the atom is now, this is a subclass of atom. It's not fitting very nicely with that atom and non-atom world, I'm just saying. Okay, when you try to come up with a small vocabulary, you get into trouble. Okay, so we'll have get arg names, and we won't really have a get body. We already have an eval. We'll just call eval on it, and eval can internally look at the body and evaluate itself. Okay, so we return back, when we enter a lambda expression, we get back an object, okay, which is this lambda atom object, and later when we have to apply the lambda object, we'll call eval on that lambda object, which will go and refer to its body. Okay, so this is information hiding here. We're not trying to go and give you direct access to the head and tail. We are giving you a more structured access, where we give you the arg names for the external, for the lambda application, because whoever's doing the lambda application has to go and change the environment of the lambda body before the lambda body is evaluated. So somebody from outside needs the argument names, and it's going to go and create a new child of the environment. It's going to provide the right environment, and then it'll just call eval on the lambda object, which will have, which will just take whatever environment has been given and evaluate its body. Yeah.
Is nested lambda also an atom, or nested atom?
Atom is something that we refuse to decompose. Not that it's not, so we are not decomposing into elements. We're not saying this is a component, first a component, second component. We are just saying we are not decomposing into children. And we are allowing methods other than get value. So we won't call it a composite atom. That's kind of a contradiction in terms. So we'll just call it an atom.
So nested lambda is also one atom, right?
Oh, nested lambda.
Yes.
So the nested lambda, yes, indeed. At the top level, yes, it's one atom. Okay.
How can you call the inner lambda as an atom?
The eval can call the inner guys eval. The lambda body can call, so the eval of this lambda is going to eval its body, right? It's going to retrieve elements from the body and call eval on it. So the body itself, internally, it will have links to the data structures. So there is a body kept. It's just not, it's not something that outside the lambda object that is accessed. We'll see. Okay, later. Questions? So we'll have a get value string which is going to just return the output that that is necessary. Okay. So again, the stored lambda expression does have the body and args. It is stored. They're just not accessible via getHead and getTail. Okay. The args are going to be accessed by the application, and the body is going to be accessed by the eval of the lambda, which will recursively go through what the body points to, and which might have lambdas in it, and call eval in it. Okay, that's what's going to happen. Okay. So in our classification, we have S expressions, composites, and atoms. And atoms we first dealt with were only int string literals. Then we added to this set of atoms identifiers. Okay. And now we are adding to the set of atoms lambda objects. Okay. So our challenge now is to take this complex input S expression and convert that into a lambda object with these operations in it. Okay? That's, okay, I've got a typo here. But that's what we have to do to evaluate a lambda expression. Take this function definition and think about this in compilers. You take a function definition, take a class description, create a class object, right? That's essentially what we're doing. Okay, except it's interpreted. So what are the cases we have? We have input expressions can be atoms, okay? Or input expressions can be composites. We know that the input expression right now is a composite. It's not an atom. That's why it's confusing, because the input expression is a composite and the compiled thing is, or the interpreted thing is not a composite, okay? So now our S was, the structure of S so far was F E1 to En, where F is an identifier atom. And we simply went and called, we looked at the first atom and went and called the evaluator for it. Okay? Now our S can be also, so now we're going to make this as F, where F is an identifier atom, and ... Something follows it. And that something may or may not be argument names, because when that F is the word lambda, then what follows it is not the arguments to lambda. It is just something to describe the lambda expression. So I'm not calling it arguments, I'm just saying it begins with lambda and it's got something else after that. It can either be a function with arguments, or it can be lambda with lambda description. So my general syntax is S is equal to F ... where F is an identifier. Okay? And why is this syntax important? Because I can just go and register a lambda evaluator. Okay, I can give that input S expression to a lambda evaluator and say, you do whatever you need to do. As far as I'm concerned, I've got an identifier, I've got something I can look up, I've got something to which I can pass the input S expression, and you go and return whatever you want to do through your eval method. Okay? So, to support lambda expressions and evaluations in general, we might have to go and change the S expression evaluator, or we might have to go eval function, or we might have to go and also add new evaluators. Here, for this part, we're only adding a new evaluator, a lambda evaluator. Okay? And the lambda evaluator is passed just something to describe the lambda thing. It's not really the arguments to the lambda function. That's why I'm just saying f dot dot dot. Okay? So far, so good? Now, so lambda evaluator is something you have to write. Okay? And to make your task easy, we've given you a helper factory. Okay? We already have a composite expression factory in integer. In theory, we have an integer atomic expression factory, and we're going to add a lambda factory. Okay? And the lambda factory, you can change it, but you won't have to change it in your assignment. So the set class is moot for you. We are going to have a new instance method. It will be your job in your lambda evaluator to extract the identifier atoms, the formal parameters. Okay? It will be your job to extract the body. Okay? Once you do that, you tell the lambda factory, here's the body, here's the formal parameters, please create a lambda object that can evaluate itself. And that lambda object will have its own eval method that you don't have to deal with. And so this is just to making the job a little easier for you to create the lambda object. Okay? So as you guys said, what is important are the formal parameters and the body, which could have been considered head and tail. So your job is to get the head and tail essentially and pass them to this guy, and this will create a lambda object. Okay? So that's a helper function. Okay? So now the question is, what does the lambda evaluator do? Okay? So the lambda evaluator is called. We know that the first entry is lambda, and we know that after lambda is a sublist. Okay? And that sublist has got P1 to Pn elements in it. And then after that sublist is another list, is the remainder of the S expression. And those are the optional expressions and then the required expression. Okay? So that's the structure. Yeah. Did I get it wrong? Yeah.
Are you allowed to submit lambda parentheses, nothing in it, just omit the parentheses at all?
Yes.
So in that case, you would be going from tail to head to OE1, OEM, right?
In that case, your head will point to, head will be nil, right?
That will be nil, so it knows that like it's empty, or do I just write nil?
So basically, it'll be a list, right? It's an empty list.
Yeah.
An empty list is represented as nil, right?
So you do have to put the two parentheses there, right?
Yes.
Got it.
Yes. You do have to put the two parentheses.
That's what I was saying.
Yeah, yeah. Okay. So your n can be 0, indeed. Again, my pictures are good for illustrative reasons, but they're often not precise. Okay. Questions? Okay. So we know that we've got this helper function, and we have to return something. So we know we have to extract the parameters. We know we have to extract the body. And what else do we have to do? That's it, right? Yeah. Call the factory. Pretty simple. Well, you have to extract the body. That's not always following these head and tail, get into trouble. That's why I wasn't even sure I got the picture right. Okay? Okay? Yeah.
So the lambda apple will have a get body.
Not visible to the world. I think I go and show what comes out. Or not here. It'll have an eval method. Okay? And a get argnames method. But it internally will store the body. But if you're talking to the Java object, I think Andrew did the right thing. He didn't expose the body because he didn't need to. If you don't need to, don't export it. Okay? So, when you go and type lambda xy plus xy, the eval method will go and create this object and it will print out the lambda, and lambda's get value to string does get value, and the get value just returns a string representation of what's internally in there. So we do know that the body and parameter information are stored in the lambda expression, because when we went into the get value, we got that information out. Okay, so the get value accesses the body, eval accesses the body, but the body itself is not ever something that you access directly. Okay? Just because we wanted to, what Andrew wanted you to, he did the eval himself. Okay, and the eval is not very complicated, not very conceptual, so that's okay. Okay, so we have evaluated the lambda expression, and in 20 minutes, maybe we'll even do the application. So, we have three cases conceptually. We have A is a variable or non-variable atom conceptually. We have a lambda expression, and we have regular function applications, we have lambda expression applications. The second and third case are really evaluation of composite S expressions, right? Input expressions. The first case is an evaluation of a atom expression. So we have to go, when we go and worry about the input lambda application, we have to basically look at the input S expression being composite. And so far I've been saying that, look, S is equal to the composite expression that is being evaluated is of the form, first I said function name arguments. Then I said some identifier name and ... arguments or lambda body. Okay, now we have another case. Now it is S is equal to a list where the first item is not an identifier. It's a lambda expression. Okay, so I can't just go up and look up an evaluator and say, you do the job. I have to do something in here to go and handle the case where the first item of the list is itself a list, and that happens to be a lambda expression. Okay? So far you guys haven't, you guys have created a new S expression. You've implemented the two string as list, etc. But you haven't messed around with the eval. Now you'll have to mess around with the eval. Okay? You have to find the second case and do the appropriate thing. Okay? So we are not talking about defining a new evaluator based on an ID. We are talking about changing the eval function itself by doing a, you'll do a subclass, which you already have, and you'll call a super method when f is an identifier. But when f is not an identifier, you'll have to do something yourself. Okay? So, this is case 1. Case 2. Case 1, we already know what to do. We have to go and distinguish between the two cases and either do case 1 or do case 2. Okay? And case 2 we have to implement. So, must change composite S expression evaluation to detect and handle the new case. Okay, this is important. Okay? But we have the machinery already. We have environments, we have a lambda atom, we have to just compose them together somehow. Okay? So, we have a lambda application evaluation, and I tried my best, but I couldn't make this, create a single picture to show the whole application. So we'll do the application in 2 stages. We look at the head of this list, and we'll go and look at the remaining part later. So the head we know is something that I'm calling lambda input, and lambda input is shown in the picture here. It's got lambda with P1 to Pn, OE1 to OEM. So the lambda application evaluation must do something with the part that's lambda input, must find the lambda input, and then must do something with the arguments to the lambda input. So let's consider what it does with the lambda input. Let's assume it's found the data structure that is the lambda input. Okay. We are going to have to apply the lambda expression to the arguments, right? That lambda expression has an eval method. So we want to we want to go and find the lambda input, okay, and convert that into a lambda object, okay? And with that lambda object, we can do other things. So the first step, what we do with the head is basically take that lambda input as expression and create a lambda object, okay, by evaluating it. Okay, so this is part of the algorithm. I'm just telling you what to do with the left data structure. So the left data structure is the input for a lambda. Okay, we want to apply the lambda. We're going to call an eval on it later. So we better have a lambda object. So we take that input, evaluate it, go and take the input, not the lambda input for the lambda expression, get back a lambda object, atom. Lambda input is an S expression, and get lambda. Okay, so we've taken care of this whole lambda thing part, and now we have to process the tape. Okay. So far, so good. Okay, lambda input just stands for this tree that I've shown here. Okay, it stands for this data structure. And this data structure we know how to evaluate already. So I've gone and stored an object for it. Questions? Trying to read your faces. Simple or making your head spin? So it calls a LambdaEvaluator. Okay, that's going to happen. It's going to go and take that input expression that's got in its head lambda. So this eval is going to call the LambdaEvaluator, which is going to return the lambda object. Okay. Now let's go and deal with. So I get back this lambda object with the methods I've just shown you again. No get body is kind of this protected method. Actually, in Andrew's implementation, he doesn't even have a get body, but conceptually, you can imagine a protected method called get body. So I took that left part, that was the input as expression. I got back a lambda object, and now I want to do things with the lambda object. Okay, and the lambda object gives me these things. It gives me get arg names. It gives me an eval. It gives me a get value. Now tell me what I should do with the lambda object. I'm trying to evaluate a lambda application. Okay, the lambda application has this lambda input that I've processed already. I've got a lambda object from it. I also have these actual parameters e1 to en, and I'm being told to evaluate. So this is S, and we're trying to figure out what s.eval should do. Okay, so s.eval, when we create the lambda object, it's got these actual parameters, actual arguments. So what should it do with the actual parameters? So somehow, somewhere, the actual parameters. So somewhere I'm going to do a lambda.eval, right? And what are we going to do with the actual parameters? By? So I need to go and assign those values in the environment, right? So I need to assign to something. I get the arg names from the lambda. Those are the values to which I want to assign, right? And I can go and store E1 to En with P1 to Pn. Works? Or the various mistakes I've made?
I mean, don't you need to make a new child environment
we should make a new child environment. Okay, we can't just do that in the parent environment. What other mistakes have I made? Nathan? I never check those things. Okay, so no error conditions here. You know, it's very interesting. I do teach exceptions, okay? But the question is, in a classroom, should you focus on the error conditions, or should you focus on the normal case? And if I was a security person, I'd be looking at all those cases. But since I'm not a security person, and this is very interesting because when I used to be a faculty member at Purdue, and when we used to grade the operating system exam, my fellow grader was a security person. So he would take 80% off if they didn't look at the error cases, and I would give them 80% if they didn't get the right thing in there. And this is a thing that Microsoft has really struggled with. And my friend Gene Spafford, who is actually a very famous guy, he used to always tell Microsoft, "Why do you implement so many features? Every feature causes, a security problem." But I'm one of these guys who likes to invent features, and so I was all for features. So this is this tension all the time. Okay, so yeah, I'm not considering the error cases. But what is something that we always ask ourselves whenever we write an evaluator? Should we do this? And what is the this that we should? What is the one question we always ask? Oh yes, Robert, what's the thing? We have to evaluate the arguments. Okay. Now this is not such an easy question. He said that we need a child environment. Okay? And now this evaluation occurs in which environment? The child environment or the parent environment? Which environment? Parent environment. We have to evaluate the arguments to go and change the child environment. Okay? So we have to go and do evals of these. And by the way, as I was walking down, this is the slide I had when I was walking down to the class. And I remembered, oh, I forgot that eval. So in fact, I came here and added that. So this is a very natural thing to miss. It's not just you guys who missed it. Okay? So we have to evaluate the previous environment, and we have to do a new child. Okay? And so we create a child environment, and it is the child environment in which we store rather than in the parent environment. Okay? And the lambda.eval is passed which environment? Child. Okay? Just putting together, Robert.
Is there a case where we need to worry about keeping track of this child environment? Or is it just when we evaluate it, the scope is free?
So we are keeping track of environments, right? This guy gets an environment he passes the one environment to something, the evals, and the child environment there, and then the child environment is what this thing has here. And the child environment is always within the scope of an application. So that application is keeping track of it.
Right.
But we don't have a global variable.
Yeah, or we don't have any way of tracking it outside of this Java scope.
Yes. And that's and we thought a lot about this, Andrew and I. But since we have a tree of environments, we're just going to store the environments in the data structures themselves. And by the way, this is not classic Lisp implementation. Okay? So we are actually, since we wanted to go towards lazy evaluation also, and funards and a lot of things, we are storing environments within S expressions, which is not the way it's done classically. Okay, but I'm really happy with the data structure he came up with. It's maybe not the most efficient data structure, but to me, we are doing the Lisp interpreter not to see how Lisp was implemented, but to understand how Lisp is precisely defined. Yeah. So I'm saying environment.store, and I'm doing a bulk store here, P1 to Pn, and assign to P1 E1.eval, assign to P2 E2.eval, and so forth, and those evals occur in the regular environment, the parent environment. Okay? Okay? Okay. Actually, even if you set child environment, the given our methods, it'll probably be have the same effect because we haven't populated the values, anything in there. So it might work. Okay. In fact, from what I can figure out, it will work. But it's misleading. We really want the parent environment. Okay. And lambda.eval is something that's given to you. I told you that's what Andrew did. But we are responsible for knowing not only what we do in our assignments, but also what Andrew did. So what do you think the lambda.eval does then? Sorry? Just goes through O1.eval, O2.eval, OM.eval. Okay, so it wasn't worth it for you to do it. It's pretty simple. But at least we have the complete picture now. Okay. The first time I've done 32 slides in so much time. Okay. So we must have an assignment due. Okay, so let's go and figure out, let's go and trace a lambda expression evaluation. Okay, so we input this lambda expression and we get back a new S expression with this structure here. And we know we are drilling down and getting the lambda input in that. And the lambda input is converted into a lambda object. So you see here in the bold, I'm just showing you at the bottom what part of the expression we're evaluating. So the lambda xy gets evaluated, we get back a lambda object, which is displayed as lambda xy plus xy. Okay? So this is just showing you this whole evaluation with traces. Now we've got the arguments. Arguments happen to be atoms here, so we evaluate them. And so that's what is showing in the picture below, that we evaluate 1 and 2, and we get back 1 and 2 back. Okay? We have to create a new child environment. So I haven't done a set queue before that, but before we do a child, we always print out the current environment. The current environment has got no variables in it because we haven't done any set queues. So the current environment is empty. Okay? The parent environment. Now we go and set the variable x to 1 in the environment, in our child environment. And so we see that we've got x is assigned 1 in our child environment. Okay? Next we go and set y to 2 in the child environment. So we are going and processing that part. Our environments are now set. We have to call the lambda.eval. The lambda.eval is looking at going and evaluating plus xy, which is the return expression. We have only one return expression, plus xy. It needs to go and evaluate, that plus needs to go and evaluate x. It looks up x in its environment, and we know that it's looked it up and it's going to find 1. Then it looks up y in that environment, it's going to find 2. And then it calls the evaluator for plus, which goes and takes 1 and 2 and adds it up and returns 3. Okay. So now you've basically got the concepts needed to do lambda evaluations. And you can relax, right? So what comes next? We know how to go and do lambda expressions, but we need named functions too. Okay? There's many ways to do named functions. Okay? The way you wrote your C Lisp, you use defun. Okay? Defun is a very restricted form of creating named functions. We can also do setQ. setQ is something we already have. So it'd be nice if we can use setQ and then assign to variables functions, and then just call those functions. Call that function. So you might think that I've done setQ f lambda xx, and I should just go and say f1 now to call the function. Okay? So what I've done is I've defined a function called f, assigned to it a lambda expression. That's stored now. I want to go and apply that lambda expression to an actual argument. I want to just name f, but I don't say f1, I say funcall f1. That's the way Lisp is designed. Okay, so I can just say, we'll have to just deal with it. Or I can try to argue why the funcall occurs. And can you guys try to figure out why I'm doing a funcall rather than just f1? I mean, why does Lisp have that?
One you talked about last class, if I store +1, 2 in a variable, and then I just write that variable, it won't evaluate it. So that's my only reasoning as to why you can't just call that, because it will just basically return what it says, then one.
Okay, if I just did f1, what syntax does it follow? It follows the syntax as an identifier and arguments, right? When we looked at function application, when we looked at, we decided that we never evaluate the f's. So when I do funcall, do evaluate. Okay? So I can go and say setQ gf and then say funcall g. G and f will both evaluate to the lambda expression. Okay? Not only that, I can just say funcall lambda. So what it's expecting as after funcall is not an identifier. It's expecting an evaluatable expression, which if it's an identifier would be a variable that's looked up. But if it's not an identifier, it might be a lambda expression, and so our funcall is much more general.
I'm just curious what happens if you literally do call f and then 1, and what happens? Where does the error occur? Does it occur because it's not an identifier?
It'll say no function definition defined for f. Okay, f is not a, just as when we did eval something, it gives an error. Okay, that's an error condition. Okay, so this is a good point to stop. You've got all the concepts for assignment 2 that we want, and it's just a funcall that we haven't seen, and that's the only other part that you will have to implement in assignment 2. So we'll do that on Tuesday. Okay, so when we got to lambdas, okay, your assignment 2 is about lambdas. Okay, we looked at the notion of having a nested environment. Okay, so we saw that we needed environments for, if we just did set queues without having lambdas, we just needed a one-level environment. When we started doing lambdas, that means we started doing functions. Each function takes formal parameters. Those formal parameters are also variables. They're not global variables, but they're variables. They need values. So they have to be in an environment. And a lambda function in general can access not only its parameters, but also global variables. So we need a form of having multiple scopes together. So we looked at having nested scopes, and that meant having pointers, having environments that point to other environments. Okay. And we saw the difference between a scope and an environment. The scope is basically, for now, just a hash table. Later, it will be multiple hash tables that associates a variable with a value. Okay. And an environment points to has a scope, has its scope, and also points to parent environments which have their own scopes also. Okay, so we have a linked list apparently here of environments, but we'll see it's actually a tree. Okay, And we call the methods on a scope as get and put because they work on hash tables. And we call the methods an environment, lookup, and assign. And lookup is basically retrieving values from scopes, and assign is putting values in scopes. Okay? And this dashed line says that if something is not found in our scope, we look at the environment of a parent and find a value from that environment, which might look at the environment of its parent and so forth. Okay? And how do we create new environments and new scopes? Given an environment, we call a method init. So it's not like a stack where you go and say stack.push. We look at the top element of the stack, if you will, and say create a new element out of yourself. Okay? And the new element then points to the previous element, so we get a linked list that way. And in terms of the assignment, the new child method I mentioned earlier was provided already by the abstract environment. That's not actually true. And that's mentioned in the assignment, that new child is something you have to implement. And the assignment talks about how to do that, Okay? But the get parent method is given to you by the abstract environment. And you have to implement the lookup and assign methods in that environment. So yesterday, Andrew put a null environment as a concrete class. That's a default environment. And you have to replace the null environment with your own environment through the environment factory to get your code working. Okay? So that's an environment. And this tells you the definition of scope. And that's something you won't change. It's just given to you. For now, the put and get methods will also not change, which is called the scopes put and get. And we saw how we must implement assign and lookup. Assign will change later, but for now we assign only to our parameters. We don't assign to global variables in the Lambda function. Okay? So we're only doing it locally for now. Okay, and that's anyway good programming, but again, we are using this Lisp as a way of illustrating all kinds of programming concepts. So we will later cheat on this, but generally it's not good practice to, it's not good practice to reassign a value in the local parameter, but global variables are also things that in functional languages, they're not a good idea to change or even access, but we'll cheat on that. Okay, so the lookup is not too hard. If you can find the value in your local scope, use it. If not, and if you have a parent and the value exists in your parent, then look up in the parent and keep following. Okay. And then the question was, when would you get more than two scopes? Okay, so we can imagine having a lambda within a global scope. So the lambda has this environment and the global scope has an environment. So when do you get multiple scopes? And that, hey, we can have nested lambdas. So we have one scope in which x is assigned 5. We have another scope in which x and y of the outer lambda have to be assigned values. And we have another scope in which the x of the inner lambda has to be assigned values. So we now have more than two scopes. So you want to go and call the parent's lookup function and not the parent's get function. Okay, because the lookup function is going to go recursively to the parent. Okay, so far so good. Again, put this in your cache. I'm going to ask a lot of questions later. Okay, and try to go and answer the questions. Okay. So that's how lambdas work from the outside. What happens on the inside? So there's two things when we look at lambdas. There's the function definition, there's the function application. Okay, so the lambda stands for the function definition, and function definition itself is an expression. So lambda expression is a piece of code that gives you back a function definition, and so that's what we're seeing here. That when the input S expression stands for a lambda with a body and parameters. That is the input. The question is, what does that evaluate to? Okay, so if you enter 5, it evaluates to the atom 5. If you enter 5, so if you enter something with a lambda and a body, and lambda, a block of code, what do you get back? and you get back this object that we'll call lambda. And we've tried to figure out whether it's an atom or not an atom. So we know that there is atoms, there are composite expressions, and composites can be lists and non-lists. So which category does it fall into? So when you're in a composite expression, it's supposed to be decomposable into head and tail, which are kind of undistinguished. I mean, it can be anything. With lambda, you've got something very specific, you've got a definition with a very fixed structure. It's not just some arbitrary S expression. So doing head and tail is just, maybe not the right thing to do. You can figure out what the head and tail are based on the input S expression. You can say the head are the parameters and the parameter names, and the tail is the body, but maybe you should just call it parameter names and body. So we want rather than head and tail. So we won't do car and cutter on them. If you're not doing car and cutter on them, then it's not really a composite S expression. So if it's not a composite S expression, it should be whatever is not a composite S expression, which we call an atom. So we'll just make it atom. Okay, maybe we need a third class, but that's what Lisp decided. So it's going to be an atom. Every atom has an eval. Okay, the eval of something like a simple atom that we're used to. Well, let's see. So the atoms we're used to are string, integer, literals, double literals. They just go and evaluate the literal. The evaluate on identifiers, just go look up the value. The evaluate on this one is going to be much more complicated. It's going to basically evaluate its body with some parameters, with the formal arguments, right? So the eval is going to be complicated. And we're going to have get arg names. The eval is going to go and use some environment. That environment is the body doesn't know anything about. The caller of the lambda knew about the environment, knew what the environment should be. So the caller needs the arg names. So we'll export the method get arg names to our caller so that we can actually create an environment to implement the body, evaluate the body. Okay, so the body will be evaluated with the environment. That environment will be provided by the caller. The caller must have the arg names to provide the right environment. So we'll export the method arg names. The body, the caller doesn't have to worry about. Just like a class, you have interface and the implementation. So the caller just needs the interface of the body. The body is needed by the eval on the lambda. So we'll just make that a protected method or just a variable in Andrew's code that the lambda accesses. Okay, so there is the input S expression, the one you entered with lambda parameter names and body, and there's the stored object. And we are showing you I'm showing you here what the operations of the stored object are. Okay, questions? So to support lambdas, okay, how do you enter a lambda expression? The first word in a list is lambda. Okay, and we know that when we have a list to evaluate, then if the first item is an identifier, we can use that identifier to look up an evaluator that does the job for us. So just as we had an evaluator for plus and car and atom and then set q, we also now have an evaluator for lambda. Okay, and that lambda evaluator will basically go and return back a lambda object. Okay, so what does the lambda evaluator do? It knows the form that is given. The first term is lambda, then we have some parameters, then we have a bunch of optional expressions. I've got a typo here. Here I should have an OEM here. And then there's a required expression. And it goes and tells, it provides a convenience function where we just say new instance on lambda factory, give it the parameter names, give it the body, and we get back a lambda object. Okay, so the lambda evaluator has to just use the lambda factory, provide it with the correct parameters, and we are done. Okay, that lambda object will have the get arg names, will have the eval, will have the get value, which we don't have to worry about. We just have to know how to use that lambda object. Okay, so as long as this toString returns the right thing, we get back a lambda definition evaluation. Okay. So, question so far? And the interesting thing here is that this is a lambda definition. We're just giving a definition. There's no evaluation really being done in the body. Okay, so with plus and other operations we saw, there's typically some evaluation going on, but no evaluation is done here. Evaluation of the body will happen later when the lambda is applied, not when the lambda is defined. Okay? Questions? So now that we have lambdas, what do we do with them? Well, we might want to apply them to some arguments. Okay? And that breaks our S expression structure. Our S expression structure said that when we are told to evaluate something, that must be a list, and the first item must be an identifier, be it setQ, be it lambda, be it quote, be it eval. And now that F could be a lambda expression. It could be something that's enclosed in parentheses and has the word lambda in it, and then is followed by parameters. So lambda evaluation is a list where the first argument is a list, or is that describes the lambda input expression, okay, which evaluates your lambda object, and the remaining arguments are the arguments to the lambda expression. Okay, so this is something if you haven't gotten to in the assignment, you have to worry about. The code can be a bit messy here. So we have now to go and change our composite S expression eval. So far we just registered the right evaluator and we didn't have to mess around with what Andrew gave us as the S expression eval. Now we have to go and look at whether the first item is an identifier. If not, go and check if the first item, then assume that the first argument is a lambda expression and deal with it. Okay? So we have two cases. Case one covered already by doing going to the basic operation manager and doing the lookup. Case two is what we have about. Okay? And what we do here is, maybe I missed out a slide here, but we have it from the previous time. So we go and figure out the part that is the lambda input, which is what the head is pointing to. And we go and say, we get that part, and that is the input expression. That's the lambda input. And we go and eval that. Okay? So that eval will involve going back to the S expression, seeing that the first term is lambda, and returning back a lambda object. Okay? So that's what the head was. So we have to go and collect the part that is the lambda expression. So the user can just type a lambda definition, and things would work as they worked before. Or they can put the lambda definition in a lambda application. If they put the lambda definition in a lambda application, we have to extract out the lambda definition from the lambda application, tell that expression to go and evaluate itself, which will be a lambda input, and we get back a lambda object. Okay? So that's what I'm saying when I say lambda is equal to lambda input dot eval. I get back a lambda object from the lambda definition enclosed in the lambda application. Okay, that's what that head is pointing to, that I don't show here, but I did show last time. And now that we have the lambda object, what do we do with the lambda object? I'm going to assign the lambda object to a variable. What am I going to do with the lambda object? This is a lambda application. What does a lambda application have to do? A lambda definition goes and returns back the lambda object. That's a definition. A lambda application will return back. It has to do abstractly, whatever level you want to describe that as. I mean, you can look at this code and think. So it has to evaluate the function. So what does that mean in terms of what we, so it's an anonymous function, you're saying an unnamed function. So that means what in terms of the Lambda object? What do the operations the Lambda object has? Does it have a car and cutter? It has, what other operations does it have? Get args, okay. And what else does it have? Just, your cache should be totally populated. I just explained that 3 minutes ago. Get the body. I said that get the body is a hidden method, and it's used by what? Used by eval. Okay. So we're going to have to eval that body in an environment that is correct for it. Okay. So yes, we have to go and call that anonymous function. That anonymous function is not some compiled piece of code. It's a code that resides in memory, and that anonymous function is represented as a Lambda object. It's an object there. That's like the compiled code. And we don't run the code. We eval it. Okay. And when you run code, you sort of set up the stack before you run the code. We don't set up the stack. We provide an appropriate environment. Okay. All of these things I said like 2 minutes ago. Okay. Yeah. So the eval is hidden from you in terms of the code you've got, but it's not hidden from you in terms of what you're supposed to know in class. Okay? So you're supposed to know all the elements of Andrew's code that I've talked about in class. Okay? But what do you think the eval does? So it's got a body. You just go and evaluate the body. The body was one expression. You would just evaluate that expression in that environment. If it's got n things in it, then you evaluate all n things in it and return the value of the last one. Okay? So that's the part that you have to use in your implementation of A2. Okay. So that's what we're doing here. You know, I mean, you should have been ideally able to answer that question without looking at the code here. But looking at the code here, you get even more clues. You see Lambda being used for get arg names, for get eval. And we are going to return lambda.eval in a new child environment. And the child environment is created by taking the environment that we were given, the environment in the Lambda application. Okay, so when the Lambda application had an environment, that environment we augment with a new environment and then go and give it to our body. So there are two environments here: the environment inherited by the application and the environment inherited by the body. And the body tends to have an augmented environment. Okay. For those of you who don't know operating systems, when you create a process, the process inherits the environment of the process that created it, and it can change it. So it's kind of that idea. Okay. And in Unix, again, the term environment is used there. That's why we use the word environment here too. Okay. Questions? Okay. And the store just goes in stores the things in this. Yeah, it stores in the child environment. Okay. So new child is like a push on a stack. Or if you've done compilers, it's like pushing a symbol table scope onto the current scope. But we don't have any pop here. And we don't have a global stack or a global symbol table. Okay? So every expression has got a reference to every application. So these are all references within data structures. Okay? And if those data structures disappear, that environment will get garbage collected in our implementation. If they don't disappear, it won't get garbage collected. Okay? So this is important again, that in our implementation, we could have had a simpler implementation where we had a global variable that is like the stack or a symbol table which you push and pop. But we are trying to go and cover many different language concepts here. And when you get to real functional programming, so far we've done functional programming like Java programming. It's just different syntax and not allowing certain kinds of operations, and yeah, making methods also be functions. But real functional programming is going to involve doing really fun stuff with environments. And so we are going to, there's no push and pop, so we can actually have a whole tree of environments, which we'll see hopefully by the end of this class. Okay? But for now, it's like a stack or a symbol table. In fact, it's a cross between a stack and a symbol table. Okay? Like a stack, you have a reference to your caller. Like in a symbol table, you go and look up your parent for something that is not in your scope. Okay, so it's a cross between that. And again, we'll break that also later. Okay. So what does LambdaEval do? That was asked. This is what Andrew does for you. Yes, it is hidden, but I'm exposing it in class. And it's given an environment, and it goes and evaluates all of the optional expressions, OE1 to OEM, and then it returns the required expression.eval environment. Okay. Now, these optional expressions can have side effects, can change the environment, so they have to be done in that order. But again, that's not really functional programming, though functional programming languages break that rule all the time. So, so we do this. Okay, questions? So this is given to you, but this is how you have to do. So let's go and try to do, let's go and try to go and apply the concepts we've seen so far. Okay, so let's do some programming. And now that we know all the implementation, at least we should understand how Lisp works. So I go and say set q. We can set q variables to values. Okay. We've looked at Lambda definitions. We looked at Lambda applications. So it makes sense to compose assignment with Lambdas. So it makes sense to go and, which we haven't done before, set q a function name to a Lambda definition, Lambda expression. Okay, and if you set q that, then you might want to go and apply that Lambda later. That's now from anonymous you become non-anonymous. So you want to go and apply that. So you might want to go and do something like this. So we went and created a Lambda expression with one argument, and then I go and call that with one argument. Okay, and what's going to happen if I type this in? Yeah. Okay, undefined function f. That's what you get in C Lisp. In Andrew's code, you might get an exception, stack trace. Okay. So what's going on here? Can we explain that based on what we've seen before?